So VTH, once again, how this formula is written? This formula, it's formula of delta V, no? Delta V between A and B. VAB we have found out, right? By voltage division and subtracting VA minus VB. VA we have found out, VB we have found out, and then we have found out VA minus VB, that is delta V, and that is the open circuit voltage VTH, right? Similarly, how RTH is found out? Okay, let's go to the bridge then to find out RTH. Since this is open, we are finding out VTH between A and B, na? And RTH between A and B. So to find out VTH, if this link is not there, these two will be in series, these two will be in series, right? So VA is found out by R3 upon R1 plus R3 into V. VB is found out to R4 upon R2 plus R4 into V. So this is VA minus VB, and we have written the formula. We have this delta V, that is VTH, right? This is the formula for VTH. How to find out RTH from this? Okay, how to find out RTH then? Let me copy this image. Okay, oh no. Sorry. So if this link is not there, and while finding out RTH, we generally what we do? We replace this source by short circuit. If this is shorted, then these two will be shorted, so that R1 and R3 will come in parallel, R2 and R4 will come in parallel. So R1 R3 divided by R1 plus R3, and is with R2 R4 divided by R2 plus R4. So this parallel combination in series with this parallel combination. So this plus this, two parallel combinations in series, and that will give us R1 R3 divided by R1 plus R3, and plus R2 R4 divided by R2 plus R4. That is RTH. Okay. And once VTH and RTH are found out, Thevenin's equivalent is drawn with VTH RTH, and then galvanometer is connected with resistance of RG, and then IG is given by VTH upon RTH plus RL, that is RG. Okay. So this is how we can use Thevenin's theorem to find out the current through galvanometer. Okay. Let's have some practice then. Example, simple example based on this one. A bridge circuit is given. Resistance R1, R2, R3 all are 2K, and R4 is 2.05K. Okay, and supply voltage is 5 volt. If the galvanometer with 50 ohm resistance, have you observed what are the values of this and galvanometer resistance? Okay, galvanometer resistance is always very less. Otherwise, what will happen? In Thevenin's theorem, if galvanometer resistance is high, then what will happen? Oh, it will load. So loading effect will occur, right? So to avoid that, galvanometer should have as small as resistance, right? So see, this is 50 ohm, whereas this is 2K, 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 and so on, right? So detector galvanometer is 50 ohm internal resistance. So let's find out then. What we want to find out is offset current delta I, that is IG, is to be found out, right? Galvanometer current. So substitute the values in the formula. R2 R3 minus R1 R4 divided by R1 plus R3 into R2 plus R4 multiplied by V. All values substituted. VTH we get it to be 30.9 millivolts. B is at higher potential than A, right? So this only changes the direction. That doesn't matter. Okay, magnitude remains same. Only direction of current changes. Instead of from A to B, now the current is flowing from B to A, right? Whereas RTH, we have just found out that parallel combination of R1 R3 in series with parallel combination of R2 R4, and this comes out to be, after substituting the values, this comes out to be 2.01 K, right? Kilo ohms, of course. And similarly, all we are using all these three formula. IG is equal to VTH upon RTH, right? So IG is equal to VTH upon RTH plus RG. It comes out to be minus 15 microamperes. So current is flowing from B to A. Normally, if it is A to B, we would have considered it to be positive. Since current is flowing from B to A, the negative sign indicates that current flowing from B to A. Okay, so this is how the galvanometer current can be found out. Now, the resolution of the bridge. This is an important factor, okay, that should be considered uh, while designing a signal conditioning circuit using bridge. Okay, resolution of the bridge. Resolution of the bridge is a function of resolution of detector. Okay, what is resolution? Resolution is the minimum change in out required in input. Minimum change required to be done in the input so that output will appreciably change. Output can be appreciably changed. Okay, so that minimum change is called as resolution. So resolution of a bridge is a function of resolution of detector, and detector can be galvanometer, detector can be voltmeter, detector can be a differential amplifier, right? So if we are considering the voltage offset, that is say we are connecting voltmeter instead of galvanometer, we define the resolution in resistance. Okay, resolution in resistance as this resolution we are defining it in terms of resistance, change in resistance, right? So resolution in resistance as resistance change in one of the arm of the bridge that causes the offset voltage equal to resolution of detector. So what minimum change in resistance of the arm, that is the sensor, will cause the change in offset voltage equal to resolution of the detector. Okay. Suppose we are using a voltmeter. Least count least count of the voltmeter is 0.1 volt. Okay, and this is used as a detector. You understand the concept? We are using a voltmeter with a least count of 0.1 volt. Okay, as a detector, right? And we have a sensor in one of the arms, say R4R of the bridge. So R4 changes and it creates VAB, or delta V is equal to VAB at 0.05 volt. Okay, since the detector has a least count or resolution of zero point 0.1 volt, it won't show any voltage because change in resistance of the sensor had generated a voltage of 0.05 volt. So that won't work. Okay, so what resolution we define is as change in resistance in one of the arms that causes the offset voltage equal to resolution of the detector. So detector should indicate the change. Okay, resistance changes and offset voltage should be changed. So we must use the detector with high resolution. Okay, suppose in the same case we use the voltmeter having least count of 1 millivolt, rather 0.1001 volt, and the change in resistance causes 0.05 change in resistance causes 0.05 volt, then surely our volt show the reading because because the resolution is 0.001 na? So change in resistance which causes the change in voltage as 0.05 volt will be indicated by the voltmeter. Okay, so the resolutions must match. Okay, for example, if the detector can measure 100 microvolt, this is the minimum measurable change in resistance that in that bridge. Okay, so we can use the following. again, equation for finding out delta V. Delta V is equal to same formula, R3 R2 minus R1 R4 divided by R1 plus R3 into R2 plus R4. That is the change in voltage between A and B, the detector. Okay. Let's have some practice with this problem. What is given? A Wheatstone bridge is given with detector D. And what type of detector is given in the problem? 3.5 digit DVM is used. DVM is digital voltmeter. Digital voltmeters are counted in terms of digits. Okay, 2.5, 3.5, 4 digits, 6 digit, and so on. Okay. So what is the problem? The bridge circuit has R1, R2, R3, R4, all resistances as 120 ohms. Bridge is balanced. Okay, and 10 volt supply. V is 10 volt supply. Clearly, the bridge is nulled. That is, bridge is balanced, right? Suppose a 3.5 digit DVM on 200 millivolt scale. What is the full scale deflection? 200 millivolt. Okay, is used as a null detector. Find the resistance resolution of the measurement of R4. R4 is the sensor. This is the sensor. Okay, so we want to find out change in R4. Okay, that will give change in minimum change in R4, that will give minimum change in DVM, right? So we want to find out delta V, suppose. It is R3 upon R1 plus R3 into V. Let's discuss the solution here. Is it visible? Can you see? Any answer? Is it visible? Are you there?
Yes, sir. Yes, sir. Visible.
Yeah. Okay. So this is the 3.5 digit DVM. This is complete digit. This is complete digit. This is complete digit. It can measure from 0 to 9. It can measure from 0 to 9. It can display the 0 to 9, but this can display 0 and 1. So the digit that displays 0 and 1, okay, it is called as half digit. So this is 1, 2, 3 and half, 3.5 digit display, right? So such a DVM, what is the minimum value? This can be 0, this can be 0, this can be 0, this can be 0. So it is the minimum value. DVM measures 0.0, right? And what is the maximum value? Maximum count of this will be 9, this will be 9, this will be 9, and this will be 1, because it is half digit. So maximum count will be 199.9 millivolt, right? So minimum count is 0.0, and maximum count is 199.9. So this is 200 millivolt scale. Okay. Hence, smallest measurement this can do. It can do if this is 0, this is 0, this is 0. And suppose initially this is 0, and if it changes, what value it takes? It will take 1. So it can change from 0 to 1. 0.1 is the smallest measurement taken from this DVM. So what is the smallest measurement? 0.1 millivolt. That is 100 microvolt. So this is the resolution of DVM. 100 microvolt is the resolution of DVM. And for this 100 microvolt change in voltage of between A and B, we want to find out change in R4. That is the resistance resolution, right? So we need to find out how much R4 had changed from 120 volt. R4 is given as 120 volt to produce 100 microvolt offset of null voltage. Okay, so let's find out delta V first. Delta V का formula R3 divided by R1 plus R3 into V minus R4 divided by R2 plus R4 into V. Delta V is 100 microvolt. Okay, smallest change, delta V, is 100 microvolt. What is unknown is R4, because R1, R2, R3 are not changing, they are fixed. Sensor is R4 and sensor resistance is changing. So what changes is R4 only. So this delta V is 100 microvolt, 120 divided by 120 plus 120 into 10 minus R4 divided by 120 plus R4. And by this calculation, we get R4 as 119.9952. Right? Initial value was R4 was, when bridge was balanced, it is 120. And now, if it has to produce 100 microvolt, that is 0.1 millivolt of voltage, just display, change it by 1. Okay, next day, then R4 has to decrease to 119.9952 ohms. Okay, so what is delta R4? Change in resistance is 120 minus 119.9952, that is 0.0048 ohm. So if the resistance of sensor R4 changes by 0.0048 ohms, then DVM will display 0.1 millivolt, right? That is 100 microvolt. So this is called as the resolution, resistance resolution. This is called as voltage resolution, right? Voltage resolution of the detector and resistance resolution of the sensor. If the sensor resistance changes by this amount, then DVM will show the change in voltage as 100 microvolt. And this is what is the bridge resolution. So bridge resolution is the detector resolution. It is a function of detector resolution. What is said? Resolution of a bridge is a function of resolution of detector. Okay? Is this problem understood then? Let me know. Any answer? Is this resolution understood?
Understood, sir.
Okay, next. The next problem. See, a sensor with nominal resistance 50 ohm, okay, is used in a bridge with R1, R2 to 100 volt with supply volt. R1 is given, R2 is given as 100. R4, the nominal value, this is the sensor, its resistance can change, but nominal value is 50. It can be 50 plus, it can be 50 minus, depending upon the process variable. Okay, so according to process variable, temperature, pressure, etc., this resistance of 50 ohm changes, but nominal value is 50 ohms. And R3 is a variable resistance. There is a potentiometer is given, 100 ohm potentiometer. Okay, it can change its value. We can change its value. Okay, it is necessary to resolve 0.1 ohm change in the sensor resistance. Okay, resolution is to be 0.1 ohm. Resistance resolution in R4 is 0.1 ohm. So what is to be found out? At what value of R3 the bridge will be null? So balance condition is to be found out. And what voltage resolution must the null detector possess? तो अगर इसका resolution 0.1 ohm है, तो डिटेक्टर का resolution कितना होना चाहिए? ओके, यहाँ पर हमने क्या किया था कि डिटेक्टर का resolution दिया था 100 माइक्रो वोल्ट हमने कैलकुलेट किया था ना, तो 100 माइक्रोवोल्ट जो कैलकुलेट किया था, दिस वाज डिटेक्टर रेजोल्यूशन and we found resistance resolution, sensor resolution. Here it is reverse way. The sensor resolution is given, sensor resistance resolution is given, and detector resolution is to be found out. And before that, value of R3 is because R3 is a variable resistance potentiometer, its value for balance bridges condition is to be found out. So that's an easy case because normal R1, R4 is equal to R2, R3. This condition is to be used and R3 can be found out, right? That's easy then. What is given? R1, R2 is equal to 100, R4 is equal to 50, R3 is equal to 100. It's a variable resistance potentiometer. Then R3 for null. How can it be found out? For null condition, R1 R4 must be equal to R2 R3. So R3 is equal to R1 R4 divided by R2. So it comes out to be 50 only. Okay. So to balance the bridge, R3 has to be, potentiometer should be adjusted to 50 volt only. Though it can be changed from 0 to 100 ohms, for balance condition, R3 should be set to 50 ohms. Now, resistance resolution of the sensor is given. So minimum change in R4 with change in process variable is 0.1 ohm, right? So the delta R4 changes by 0.1 minimum. Okay. If we consider before change and after change, we can nominate it to be delta R4 as R42 minus R41, right? So R42 has to be R41 plus or minus 0.1. This is 0.1. R41, if it is the initial value, then minimum change is plus or minus 0.1 ohm. So this becomes R42. So nominal value, that is initial value, is 50 ohm. It is given, R4 is given as nominal value 50. So considering it to be changed to be negative, it will be, you can consider it positive. It is not specified. You can consider plus sign, you can consider minus sign. Okay? 50 minus 0.1 comes out to be 49.9. So change after change, R4 value is 49.9. And now let's find out corresponding change in offset voltage, delta V. And we know the formula for delta V, R3 upon R1 plus R3 into V minus R4 upon R2 plus R4 into V. So delta V comes out to be 0.444 millivolt. Okay. So when the resistance of the sensor R4 changes by 0.1, then the detector voltage changes by 0.444. So this is the resolution of the detector. This is the resolution of sensor. This is the resolution of the detector. Okay. This way, the resolution can be found out. I think the concept of resolution is understood. Is it? We took it both way. We took it both way. First, we took this problem wherein the detector resolution was given and resistance resolution was to be found out. Here in this case, resistance resolution is given and detector resolution is to be found out for the corresponding value. Okay. Now, a difficulty in using these bridges. Okay. One of the problems in using the bridges is the lead resistance. Okay. Do not go by control system theory. This is not lag and lead compensation. It's not that. Lead meaning the connecting lead. Okay, connecting wire. Okay, when a sensor is to be used, it has to be connected in the bridge. And many a times, what happens, the bridge is at other location and the sensor is at some other location. Suppose we are measuring the temperature of a motor. Okay, so and the temperature, it is blower is run by an induction motor, and we want to control the temperature, rather measure the temperature of the induction motor, right? So the sensor, resistance sensor, let it be thermistor or RTD, it has to be in the motor near the winding, right? And then the wires, connecting wires or connecting leads are to be taken from those sensor, RTD or thermistor. They are to be taken out of the motor, and there will be a certain panel in which the bridge circuit will be there, and then those terminals are to be connected as in the one of the arms of bridge. Okay, so what happens, the connecting wires or leads also possess certain resistance, and that is comparable with the sensor. Okay, if it is negligible, the connecting leads resistance is negligible, then it doesn't matter. Okay, but if it is comparable, then that will disturb the output of the bridge. That will affect the output of the bridge. It will have some effect on, and the readings of the bridge output offset will be wrong. Okay, it can be misleading. So what happens in many process control applications, the bridge is located at a remote distance sensor. Okay, as I said, if it is a fire alarm, okay, using some type of resistance, okay, so that resistance is at site, and those leads are to be taken at the control panel. So wire has to be run from two wires has to be have to be run from those site location of the fire alarm to control panel. Okay, so as this length increases, the resistance of the leads also, wire connecting wires also increase, right? So in such cases, resistance of connecting leads should be considered in calculation of the offset and resolution. Okay. Another problem of the remote location of the bridge is that change in lead resistance due to change in frequency, temperature, stress, and chemical vapors. Okay. So this resistance of the leads are also made up of the conducting materials, na? Okay, like copper or some aluminum or something like that. So these leads, rather silver coated or some other material, right? So these leads, resistance of these leads also change with frequency, temperature, stress, and chemical vapors. So if this resistance is not constant, the output of the bridge will not be predictable at all. Okay? So these readings of this detector will be absurd reading. For any type of change in the R4, it will not give consistent readings. Sensor material is different, lead material is different. So change in resistance will not be same for both, and that may give false answer or false indication here at the detector. Okay, so it may lead to errors in the reading. Now, so this lead resistance, there are many methods of this one. Okay,